The title of today's event is How Humans Came to Construct Their Worlds. My talk offers a literal and comprehensive answer. The answer is with energy. Energy is defined dismally by physicists as the capacity to do work. But in fact, it's the capacity to do anything at all, including to think with our large, energy-hungry, energy-inefficient mammalian brains. My topic today is the construction and running of buildings, which today consume 30% of all the energy that humans use. Larry's astonishing discovery of timber construction hundreds of thousands of years ago suggests a long prehistory of the story I will tell, which is squashed into just the last 14 or so thousand years, from which almost all known evidence of buildings dates. This is a reconstruction of a home built in Ukraine 14,000 years ago, one of the earliest houses to leave a substantial trace. And already energy is the answer to all questions about human construction. This was built in the Ice Age in the frozen steppe, so its purpose is to keep in heat energy from human bodies and from a central fire to allow humans to survive the cold. It's built there so that the people who made it could pursue the rich food energy resources of mammoth and reindeer into an inhospitable climate. And it's built of energy byproducts. Mammoth bone structure with reindeer hide enclosure over it, making for a kind of weighty tent. There's even evidence that they burnt mammoth bones to heat it. Energy, energy, energy. This one-to-one correlation between buildings and energy system continues through the energy transition to farming societies and the cities and states that came with them, which we're hearing about today from Trevor, Ricarda, and Michael Smith. Where hunter-gatherers optimize their access to naturally occurring energy sources, farming societies reshape the landscape to maximize the production of crops grown for food energy and firewood grown for heat energy. Productive farming societies almost all ended up with a steep social hierarchy, a small elite controlling the distribution of the grain energy grown by the other 90% or so of the population. For this small elite, labor was extremely cheap. Walter Scheidel has found that for 3,000 years from 1800 BCE, unskilled building labourers across a wide range of farming societies would work for little more than the cost of enough food to keep them going and get them back to work next day. The building projects commissioned by the grain-controlling elite could therefore be very big indeed. Here are some of them, drawn by Gingerhead Limited for my book, all shown to the same scale as the mammoth hunter's home at the top left. The biggest of these, the pyramid, built as a tomb for the Egyptian pharaoh Khufu around 4,500 years ago, weighed nearly 6 million tons and took around 72 million days of human labour to build. But Khufu had the grain and the workforce. From his perspective, why not build a 6 million ton pyramid? Whilst labour was cheap in farming societies, however, intense heat was expensive, coming as it did from trees which grew very slowly and burnt very fast, having locked up a lot of land for tens of years as they grew. This meant that even the giant projects of the farming millennia tended to try to use labour rather than heat where possible. They carved stone rather than firing brick. They reused materials wherever they possibly could. They built with timber rather than burning it to make other materials. The astonishingly refined wood joining traditions of so many farming societies reflect the fact that it was more economical to learn to carve two big beams like this to fit together this precisely than it was to burn enough wood to make an iron nail to do the same job. This scarcity of heat energy throughout farming history meant that even a building like the Baths of Caracalla in Rome, here to the same scale as the Pyramid of Khufu, a stomping fist celebrating the emperor's mastery over nature and humanity, even this was discreetly more economical than it looked. Despite some conspicuous bronze fittings, more than 94% of the building's volume was made up of materials used as found, rather than being heat processed before use. Transport energy was quietly minimized too, whilst the cladding stones, long since removed for reuse, were transported from as far away as Egypt to show off energy expenditure. In reality, more than 3/4 of the materials for the structure hidden behind that opulent cladding were sourced from within just 20 kilometers of the site. These long-established rules that labor was cheap, heat expensive, changed quickly and completely with the rise of fossil fuels. Where firewood locked up land and grew slowly, coal, and later oil and gas, took up very little farmland to extract, and their mining could be scaled up almost limitlessly to meet market demand. The total amount of energy available also shot up. A 19th century coal miner could extract 2,500 times more surplus energy for society than a medieval European farmer. And this meant that heat rapidly became cheaper than labor. And you can see that very quickly in Georgian houses, where heat-hungry bricks and iron railings were cheap to make thanks to coal, and quick and simple to deploy on site, saving expensive labor. Under these new conditions, cities expanded at an alarming speed, freed from the ancient limits of firewood as heat energy. London's 19th century expansion is depicted in this cartoon as a military defeat of the countryside by the advancing army of bricks and mortar. Coal energy supported massive colonial expansion and powered the machines that processed commodities into finished goods at a scale that encouraged the brutal harnessing of people and land around the world to produce the cotton, sugar, and other raw materials on an entirely unprecedented scale. The result of this new picture, cheap fossil fuel heat, expensive labor, has been a 4-century process in which vast amounts of human ingenuity have gone into swapping out human effort for fossil fuel energy. The first thing to convert to fossil fuel was simple heat functions, making glass, making bricks, making iron, and later making cement and steel. Today's global energy supply for making cement alone is from fossil fuels. If instead you wanted to grow a forest big enough to provide that much heat, the medieval way, you would have to grow trees over every square mile of the continental United States to meet the world's contemporary demand for heat for cement alone. Concrete and steel, aluminium and plastics multiply this up, and they're only usable on an architectural scale thanks to cheap fossil fuel energy. They cost too much energy to use in a world without fossil fuels. From the late 18th century onwards, the steam engine began a second wave of substitutions, swapping cheap fossil fuels for human muscle power in transport and manufacturing. And these two revolutions ushered in almost everything in today's architecture. Heat-hungry materials, concrete, steel, and glass, tested out in modernist villas, then spread to enormous megastructures built all at once at great speed on huge areas of demolished city. Everywhere that fossil-fueled architecture took over, long traditions of natural shading and passive comfort were abandoned in favour of uninsulated, open-plan spaces, tested out often not too successfully on the villas of the rich, but later rescued by extensive, powerful servicing allowing habitable spaces with no natural access to light or air to be comfortable deep underground. It also allowed buildings to be clad entirely in glass in all climates. Can you tell which of these two is in Alaska and which is Saudi Arabia before I let you see which one has snow on the ground? Increasingly narrow definitions of comfort became a sign of prestige worldwide, with Western business clothes worn from air-conditioned house to air-conditioned car to air-conditioned office as a worldwide mark of a successful life lived in fossil-fueled opulence. Car-based planning, using the internal combustion engine to convert chemical energy cheaply from fossil oil into heat and motion, spread out populations over ever larger areas. This brought the immediate pleasures of more space, but it depleted the supply of local cafes, shops, and eateries that come with density. And now, a third energy revolution is well underway, with human clerical and mental work joining our physical work in being transferred rapidly to increasingly capable machines. We will hear from Michael Fox about the latest phase of this, where artificial intelligence is starting to transform both the design process and the running of buildings. And with it is coming another leap up in the fossil fuel consumption of the building sector. At present, AI's energy requirements are doubling every 100 days. And the pressure to keep building more and more data centers to keep up with the information revolution is leading to unscrupulous practices and significant strain on local resources where they are built. Thanks to Michael Arbib for sending me this New York Times article on the subject. Very good. All these high energy developments can be exhilarating, and they've led to many wonderful buildings, including the Salk Institute by Louis Kahn, which I'm grieved not to be visiting in person. They've led to material improvements for a majority of the world's 8 billion people. Even the relatively poor in the informal settlements of Central and South America, which Christine is researching, dispose of vastly more energy resources than the poor of any earlier period of human history. And the enormous improvements in urban life expectancy that have been achieved by sanitation and public health science are precious. But now there is a problem. Unbeknownst to all involved until very recently, the carbon emissions and other environmental impacts of so much heat-intensive construction is proving to be more than the planet's ecosystems can sustain. My title is Energy in the Balance, but our energy use today is very far from being in a tenable balance with the natural systems we depend on for our survival. How humans construct their worlds right now is by burning fossil fuels. The construction and operation of buildings is responsible for 37% of greenhouse gas emissions, and the building sector is so far, according to one of the authors of the latest IPCC report, talking to DZine, the worst performing of all sectors in taking action to reduce these harms. As things stand, climate change harms are hitting faster and harder than predicted even a few years ago. And credible estimates suggest that there could be over 1 billion climate refugees moving away from uninhabitable regions within the coming 25 years, seeking homes and jobs in the areas less badly affected. If we make that happen by carrying on building and living as we have been, it will be the largest migration of humans ever seen. And it's currently hard to imagine it being peaceful and orderly. Over the remainder of the century, things will worsen considerably from there if we carry on as we are. So what do we do to avoid climate catastrophe? The answer lies again with energy. Energy has been completely central to how humans have constructed their worlds so far. And a transition to renewables will not involve one-to-one substitution of renewables for fossil fuels. They are very different. What's needed instead is a new architecture for a new energy regime. Existing buildings need to be reused, if at all possible. New buildings need to be made of natural materials without heat processing or long-lasting toxins. Buildings should be adapted to make you comfortable enough with little or no heating or air conditioning, rather than, like the international hotel room, being cooled or heated into a characterless sameness worldwide, a homogenized beige sausage of life-shorteningly forgettable existence, bought at enormous energy cost. As we reconstruct our world to avoid climate catastrophe, we should all surely be asking ourselves and each other about proportionality. It should influence every decision we make, from what we build and how we build it, to how we vote and what charities we donate to, through to how we get to work, what we have for lunch, where we go on holiday, and so on. In all things, the same question should guide us. Are the present gains proportionate to the harms they are causing in the near future? In architecture, this question is particularly urgent and crucial. What gains in comfort or performance could be worth continuing to take responsibility for 37% of the accelerating climate crisis? What marvels of artificial intelligence or improved indoor air quality are proportionate to the ecological harm of increasing energy use for making and running the kit? Which claimed savings are genuinely reducing the sum total of emissions, and which savings are merely a percentage reduction on something that's actually an absolute increase in emissions? If, when thinking about climate change, you feel your individual actions are irrelevant, dwarfed by those of, for example, Chinese industry, reflect on this. Firstly, US people can make more individual difference than almost anyone else. Any 7 average Americans today together use in their lifetime more energy than it costs to erect the 6 million ton pyramid of Khufu. Modern people in the long industrialized world are astonishing outliers on the graph of human energy consumption. And whilst our material amenities are proportionately remarkable, there is little evidence that our happiness has risen with them. Secondly, if you don't believe your individual actions make difference ecologically, do you vote? Because any time an election is decided by a margin of more than 1, your vote made literally no difference. Whereas in carbon emissions, reducing your emissions even slightly genuinely does reduce the total CO2 in the atmosphere. And the influence of your actions on your family, co-workers and friends multiplies that effect rapidly. Above all, if you can help to prevent the construction of a typical new building of concrete, steel, aluminium, plastic and glass, you will make a more positive difference than through any other action in your power. For comparison, by cancelling the construction of this proposed new building in London, you would save 40,000 tonnes of carbon dioxide. You could otherwise save that amount of carbon by personal action, taking cold showers every day instead of hot. Not an appetizing prospect in London, but it saves energy. To save that same 40,000 tonnes of CO2, you would have to take daily cold showers for over 680,000 years. Let's make the change we must make, and make it now, through how we construct our worlds. And let's get energy back into balance with nature. Thank you.